All right, this is the second Money Button documentation video in our documentation series. It's all about Money Button itself, but not just Money Button, also a lot of the sort of underlying properties of Bitcoin and the tools that we're using to make it possible to do Bitcoin stuff. So what we're talking about today is elliptic curves. So last time we talked about big numbers, and you need to know something about big numbers to know something about elliptic curves. So what elliptic curves are basically is, it is a sort of a branch of mathematics that is about these particular objects that are just called elliptic curves, and we'll look at this in a second. And it's used in asymmetric cryptography. So the idea of having a private key and a public key uses this. And the history of crypto goes back a long ways, but if you go back to the 1970s is when the idea of asymmetric cryptography was invented. And it was later on discovered that you could have more efficient cryptography using elliptic curves. The property that matters most for Bitcoin is that the size of your keys are smaller. And so you can do things like, it's more efficient to communicate a public key to people using elliptic curves than it is with these sort of old style RSA and prime number based approaches. So let me start by, so we're going to cover just this, what is the class in BSV, which is called point, and points are points on an elliptic curve, and you can add them and multiply them. But before we do that, let's just briefly look at this blog post here. So I'll share my screen and look at an overview of what elliptic curves are. All right, you guys see my screen?
Yes, perfect.
Okay, so this is just a blog post. There's a lot of really good resources, so we'll share more than just this blog post. This is just a simple one to get a really high level overview. So this just covers what it is, what it's for. It's used in elliptic curve cryptography, uses elliptic curves. And elliptic curves are based on this equation. So an elliptic curve is like a squiggly line here like this. And it's based on this equation. And they have this unique property. So what you do is, for people that aren't familiar with advanced mathematics, I'm going to give the briefest possible description of group theory. So everybody's familiar with things like numbers, and you can add numbers together and multiply numbers. But actually, there are other objects out there that you can have an operation defined on the object and get a new object. And sometimes we call this adding, even though you're not really adding things, you're doing something else. So in elliptic curves, what we do is we start by defining what this is, and it looks like this. Then we want to define an operation, and this is showing you 3 different points on here. And it doesn't look like they have a photo of it, but we'll have other resources later. There's a new operation defined on the curve, which involves adding 2 points on the curve together and how to get a new point. So it works where you say, can you see my mouse? I don't know if you can actually see my mouse. Does that show up for you guys? Okay, no, so unfortunately you can't see my mouse. I'll have to explain it in words here. But if you look at P on this chart here, that's a point, and then Q is a point and R is a point. What you do is, in order to add P to another point, you draw the intersection and then you flip it over and find the point. So you can't see my mouse, so it's hard to explain, but again, we'll share other resources here. The point is that you can add 2 points together and get a new point on an elliptic curve. Now, you do another thing here. So a curve is like this continuous curve. In cryptography, we need a finite version of this curve. And so what you do is you use modulus arithmetic. And instead of having this extend off to infinity, you have the points are actually defined on a finite field. And so you would end up with actually a grid of points. So this will become a little bit more clear later on. Okay, so now you can do basic operations like you have things like a number, which is D, and then a point on the curve, which is P. Now, you can add 2 numbers together, you can add 2 points together to get a new point. Again, using this other operation. Again, we'll cover this. We're going to go through examples, so this will be a bit more clear when we actually cover it in a second here. But you can multiply, and multiply means adding a number of times. Just like with numbers, if you have 2 numbers, 1 and 1, you add them together. It's the same thing as multiplying by 2. So if I have the number 1, I add it to itself 5 times. It's like multiplying by 5. If you have an abstract operation, you can do the same thing. You can define multiplication as a series of additions, so to speak, and get a new value. And I'm not going to cover the encryption and decryption because that's not relevant to Bitcoin, at least not inside the protocol. Okay, so that was probably, that gives you the world's highest level intro. We'll share other videos and stuff like that. There's a wonderful video that we can share that explains this in detail. But let me move on to showing you guys my terminal so we can start connecting this to the real world. All right, stop screen share. And I'm going to share my screen again. And we'll go into my terminal. Let me make sure this is working first. Okay, and okay, you guys should be seeing my terminal right now. Okay, before I continue, based on that, that was obviously super high level, but do you have any questions? So I'm going to start showing examples how to actually use the library, but do you have any questions before I start doing that?
No, I believe that it's better to start seeing examples.
Okay. Okay. All right. So what I'll do here is, so I'm in my terminal here and open up Node and say something like, let me load the library. So we have this object called a point. So a point is a point on the SECP256K1 elliptic curve. And what I can do is I can do things like this. There's a point that's called the base point, which is G. This is a point. It has an X value and a Y value. So it's a point just like you would think normally for mathematics. It has two values, X and Y. The trick here, though, is that the way that you add them is different. So I can do things like this. One of the simplest things I can do is actually add G to itself. So G is a special point. It's called the base point. And what you can do with G is every single other point on the curve can be generated by G. So let me try and explain what I'm talking about here. So if I have G, I can then do things like, so I just added G to itself and I produced a new number. So first of all, is that part clear? I use the add operation to add this special point to itself. I get a new point, X and Y. Okay, and it's different.
This new point also belongs to elliptic curve.
Yes, correct. Exactly. Exactly. And this is where there's this field of study. Again, I'll link to all this stuff because there could be like literally an entire semester long course just on this, right? Like that's how complicated this is. But the idea here is that that is a basic property of a group. You add two of them together, you get another element in the same group. And that is definitely true for elliptic curves. So I could add this to itself. I could actually keep adding it if I wanted to. It's kind of instructive to think of it that way. So I've added it to itself one time. I can then add it to itself again as many times as I want to, actually. Here, sorry. So now I've added it to itself 3 times. Okay, so I now get yet another new point. Now what I'm doing there when I add this same number to itself 3 times, or sorry, the same point to itself 3 times, that's as though I'm multiplying it by 3. So even though this add operation is abstract, it's not really simply adding. If you tried to add the numbers together, you would not get the same answer. It is an abstract addition operation. That's just the operation on the group. Now, I can then define what it means to multiply by saying I just add a number to itself a certain number of times. So like if you were to write this down, I could say something like, and well, again, when we look at the documentation, I wrote some of this down already, but you get the idea here that if I have a point G, I can then do things like, G plus G is adding it to itself. And then I can do 2G equals G plus G, right? So I can define multiplication as a series of additions. And obviously 3G would be G plus G plus G, as many times as necessary. Now, it so happens that G has the property that you can add it to itself as many times as you want to. And every single point on the curve is G added to itself some number of times. So any other point I have on the curve, suppose I have something like P, there is always a value A such that A times G is P, okay? So this matters because we'll see in a second here about sort of like private keys and stuff like that. So built into the library is the ability to multiply. So now what I can do is I can have the point here and I can actually multiply it by a big number. So what I'm gonna do here is I'll do a really sort of a simple big number. So I'm gonna, sorry here, I said add, but I mean multiply. So I'm gonna multiply G by 1 to, okay. So let me print out G, crypto.getG. And what I just did there was I multiplied itself by 1, and it gives me the exact same answer back, which is what I would expect. So multiplication by 1 gives me that answer. I should now be able to multiply by 2. And this should be the same thing as adding it to itself twice. Right? See if that worked out correctly. So adding it to itself twice gives me the same thing. Okay.
What happens if you multiply by 0? It should result in 0.
I don't know. Let's see what happens when I multiply by 0. Point dot. Let's see. Actually, I'm not sure you can do that, because the thing is, there isn't really a 0. So you can only like add. Okay. Okay. Let me try it here. So I can multiply by the 0 though. So let's just see what happens when I multiply by 0. bsv.crypto.bn.from number 0. I get to infinity. Interesting. Okay. So there's a special infinite point there.
I was guessing have no value, but infinity was the opposite thing.
Yes. Every value. Okay. So basically, I think that's a. So I'm not sure what the significance of that is. Like that wouldn't be. There are cases like if you look at how some of the cryptography algorithms work, they have to check for a point at infinity, and if you get a point at infinity, things are broken. And so just like you would normally expect in mathematics, like, you know, it's sort of that's a sign that something has gone wrong most of the time if you get infinity. Okay, so that's interesting. Okay, so now what I can do here is now we'll cover this several times because it's related to how Bitcoin itself works. But what we can do is I can now do things like generate a private key. Okay, now a private key, I'm going to do this similar to how I did before. I'm going to generate a random number, which is my private key. So bsv.crypto.random.get_random_buffer size 32. Okay, so I have this pbuff here is a buffer. It is a long random number written in base 16. Now what I can do is I'm gonna generate my private key, lowercase p here, is going to be a number. So I'm just going to say bsv.crypto.bn.from buffer pbuff. Okay, p.toString. This is what it looks like as a number. So it's just I've just generated a random new private key. So I'm not going to put any money in here because people could take my money because they can see the private key clearly on the screen. So now what I can do is I can actually generate the corresponding public key is actually the private key times G. So the way you would write this down mathematically would be like this: P equals little p times G. That is a public key by definition. Okay. So I can make P by saying something like bsv.crypto.point .getG .mul by little p. So p.to, let's see, I think there's a toString here. No, here, let me just print out p directly. It shows it to me. Okay, so this is the public key. Okay, so I just generated a public key from a private key. That's how you do it. Now, you would not normally do it this way inside of this library because we actually have classes for private key and public key. And they have additional formatting tools and things like that. So you wouldn't do it this way normally, but this lets you understand what is actually going on under the hood. A private key is a big number, and a public key is a point. So a private key always consists of a single big number, right? Or I do, p.toString or whatever, and look at the number. It's just a number. It's a really big one. I then can look at my public key, and it's always a point. So I can do things like get x and get x.toString. So a public key consists of two values, an x value and a y value, and they're ludicrously large numbers. But this is a point on the elliptic curve, and the elliptic curve used by Bitcoin is SECP 256K1. It's a specific curve with specific parameters chosen, and a number on this curve, or sorry, a point on this curve is not necessarily on a different curve, but that's the idea. And so this point class that we have, bsv.crypto.point, is all the points on the SECP 256K1 curve. So the next thing I can do is basically show our documentation. You guys have any comments or questions about that before I move on to the next thing?
Just one. So basically, every time that you see a public key, it's actually true values that are encoded in some special way, basically.
Yes.
Okay.
So it's usually two values. So it's a good question, because there's actually a notion of a public key that is compressed. And so the way you actually see it most of the time in a Bitcoin transaction is actually a compressed public key. The difference is that a point technically is both an X value and a Y value, but a compressed public key is the X value and a number indicating whether the Y value is odd or not. Because it turns out that in elliptic curves, you have this, or at least this curve, you have this property that you can derive the Y value from the X value if you know whether it is odd or not. So that's a long-winded answer, but this is why you see in Bitcoin, you actually see public keys are 33 bytes, because it's a 32-byte big number plus an additional byte indicating whether Y is odd or not.
Cool.
Okay. All right. Let's switch to, I'm going to stop screen sharing again here, and we'll switch to looking at the actual documentation that we have for this. So one more second here. Okay, you guys see my my browser again here?
Yes.
Okay. Okay, so what we have here is, so I wrote this yesterday, and for people watching this video, yesterday will no longer be true, but as of today, that's true anyway. This is just a summary, basically what we just talked about. So it's like an engineer's level summary, the stuff that you should know to be an engineer. But again, like elliptic curves is like, you need to really know like group theory and things like that, and it's a quite large field of study. But we don't need to know everything. All we really need to know about is that, you know, a point is an X and a Y value, and you can have, you know, more than one of them on the curve here. And a public key is a point that is a private key times G, always. And then it turns out that once you understand the basics, you can understand something called Diffie-Hellman almost trivially. Diffie-Hellman is the idea that you can generate a shared secret with someone. And this is extremely easy to understand. It's cool that Diffie and Hellman get their names attached to this, because once you understand all the basics, it looks like it's almost trivial. And what it is if Alice has public key A and private key little a, and Bob has public key capital B and private key little b, Alice can take her private key, so no one knows her private key, times Bob's public key, and then you can rewrite this as, okay, well, capital B is little b times G, then rewrite that because they are commutative, and then I can see that little b, that is now A, so that is A. So that is actually the same thing as Bob's private key times Alice's public key. This is Diffie-Hellman written in the world's most compact form is what this is. And so this is a shared secret. So long as Alice and Bob don't share their private keys, they can generate a number, which is this number. Alice finds the same number by multiplying her private key times Bob's public key. Bob finds the exact same number by multiplying his private key times her public key. Same number. Now this is a point. It's not really a number. You can convert it into a number by taking the hash of it. Okay? And so a lot of things, what you do in Diffie-Hellman is like, we want to arrive at a shared secret. And so we use Diffie-Hellman to come up with a shared secret. We hash it to convert it into a number. And now that we have a number, we can do all sorts of interesting things with it. And this will be relevant when we come back to BIP32 later, because this idea is where you generate new numbers and add them together is used inside BIP32. Diffie-Hellman is kind of its own separate thing, which is used inside of our ECIES library. So this will come up again. Like we'll see that this is not just math for the sake of math. This is like used extensively throughout Bitcoin itself. It's used inside tons and tons of high-level protocols based on Bitcoin. Okay, and then the rest of the documentation just describes the stuff that we sort of already talked about here, how to get G, how to multiply it by a number, and showing you, you know, all the basics here. And the things that you basically need to know about, there are a few other subtleties like the compressed points that are not written in the documentation, but The things that are most important are simply you can add two numbers together and you can multiply a number by a big number. And that's it. What do you guys think? Any questions or comments about any of that stuff?
No, I believe it's clear. It's like one of the things that are really under the hood, right? Usually you just work with crypto and don't see with Bitcoin, and you don't see any of this on these things basically.
Yes.
So it's cool to know how they work.
Yes, it's something that you normally don't need to, like, it depends on what you're programming, but we're still at a stage where, like, we're going to be creating new protocols based on Diffie-Hellman, for example. Yes. And so understanding what is Diffie-Hellman is a necessary prerequisite to design a protocol that uses Diffie-Hellman. And, you know, things like that, it's just elliptic curve cryptography. It's all based on those ideas. And so all these things will show up again. But yeah, basically, if you're building like an app, at some point, I mean, basically, it's already the case that you can do things like build a Bitcoin wallet without understanding this, because the tooling is good enough that you don't need to understand this. You do need to know what a private key is, but you don't need to understand all the math and whatnot underneath it. But for these other protocols that we'll be building, like when we do things like identity, we're going to be doing things like finding shared secrets, signing messages, encrypting things based on these ideas.
You mentioned RSA. Can you summarize what do you recommend to use elliptic curves instead of RSA?
Sure. So, okay, so cryptography has a long history, and it was usually about encrypting things. I wanted to be able to hide my sort of data from other people. I wanted to be able to send a message to someone privately. And originally there was this idea of symmetric cryptography, which is the idea that we have a shared key, that I can encrypt a message, and so long as you have the same key that I have, you can decrypt my message. Now, it was later discovered that you can start doing all sorts of interesting things with hiding information and doing things that are more advanced than that. So the problem with encryption with a shared key is that you have to distribute these shared keys somehow. And so in the 1970s, some people, it was, I don't know all the long list of people, but RSA is actually a list of initials of some people that figured out a particular way to do this, and it's just called RSA. In fact, it was actually patented, if I remember correctly, originally. And they published on it and all that stuff. And they had a whole company that still exists called RSA, is that company. And it's the idea that you have something where you have let's see, you still have this idea of private keys and public keys, but it was all based on prime numbers and modulus arithmetic. And so you would do something where your public key was, I can't remember which way it goes because I don't remember this as well as elliptic curves, but it's something like you pick two prime numbers that are very, very large, and you multiply them together to get a new number that you then share. So it's like the number can be factored into two prime numbers. And the number that you pick is so large that no one can figure out what are the prime factors. It has exactly two prime factors. And no one can figure that out because they're just too big. If you run the factorization algorithm, it takes way too long. And then you do something where you have a bunch of modulus arithmetic where something involving you, I forget exactly, you encrypt, I think you encrypt by, somehow there are other prime numbers involved. I'll have to link to resources because I can't remember off the top of my head. But anyway, the point of all this is that you had this case where your keys were these very, very, very large numbers that were actually quite large. And in order to have good security, they had to be extremely large. So in RSA, for the equivalent of something like 128 bits of security, you have to have a 2048-bit key. So it's like, roughly speaking, 10 or more times longer than sort of the amount of security that you have. And what elliptic curves allow you to do is you can have the exact same level of security with substantially smaller keys. So instead of having a 2048-bit number that you're sharing around, you have a compressed public key, which is 33 bytes, or that's like 200 and something bits. So it's basically 1/10 as big that you're sharing around. So that's basically it. That plus there were, that's really basically the answer. And it's also fast and all that stuff. And so it's really ultimately about having substantially smaller keys, which allows you to do things like put them on the blockchain and save space.
I'm sorry. So reduce complexity, but not compromising the security.
Exactly. Yes.
Yep.
It makes it significantly smaller size keys with the same level of security.
Right.
Okay. Well, then I guess then on a final note, so we have, please visit moneybutton.com. You can see links to all this stuff, documentation, our Telegram group. So you can visit the documentation directly at docs.moneybutton.com. And if you have questions or anything like that and need help building things with MoneyButton or with BSV or library, visit our Telegram group at t.me/moneybuttonhelp. And we'll provide links to all this stuff in the video notes. All right. Did I forget anything?
No, everything was said.
Everything said, yes.
Okay, great. All right. Then talk to you guys shortly here.